Welcome back to Robot Cantina. Grab yourself an ice-cold beverage, sit back, and relax, because that's exactly what I'm doing today. Oh yeah, episode 17. Well, it's missing from our lineup, but don't worry. We assembled a search and rescue team, and we're actively looking for that episode. Well, I almost did it, and that is I pushed too hard and almost ended up in the hospital again. Now, don't worry, it's nothing too serious. It's just a minor case of stupidity. And, as I understand it, there's a lot of that going around. Anyway, as most of you folks know, about 6 months ago I moved from rural Michigan to small town Kansas. Not really much of a change, but it is a bit hotter here in the summer. As a matter of fact, in our studio workshop, it gets plenty hot during the day. Typically, inside the building, it hovers around 90 to 95 degrees Fahrenheit, and some days it can get a little bit hotter. So, I don't always check the thermometer, and sometimes I forget to drink enough water. Well, you get the idea. So today, I'm still under the doctor's orders to take it easy, and that sucks because I really can't sit still for long. So I reckon we're going to play around with a little project that I've been working on, and if it all goes well, we'll get to use it in our next video. And what I'm talking about is modifying the throttle on our Saturn to be computer controlled, sort of a robotic throttle, I guess. The theory is, if we automate the throttle in the Saturn, we can possibly get better fuel economy and more consistent results with our tests. Of course, we won't be reinventing the wheel. Pretty much all modern cars have automated throttles, but ours will be a little bit different in the way it functions. Ours, we use additional signals that will automatically optimize the engine performance to maximize fuel economy. Today, we're just going to cover the basics, and in the next episode, we'll actually get to drive the car with the automated throttle, and that should help out with our lean burn experiments. So let's take a moment and talk about how we're going to automate the throttle body. So here we have a normal throttle body off a Saturn 1.9 liter engine. Over on the side of the throttle body, we can see the throttle position sensor, and of course this thingy here is the throttle, which is normally connected to the throttle cable. Let's take a look at this throttle body in its normal habitat. Alright, so here we can see the throttle body is mounted to the intake manifold, and the throttle thingy that we were just talking about is right here. And of course, here's the throttle cable. Now this throttle cable goes inside the cabin of the car and is connected to the accelerator pedal. And pushing down on the accelerator pedal pulls on the throttle cable, and boom, the throttle opens. Believe it or not, this is the old school way of doing things. I reckon you can't find a modern car nowadays with the accelerator pedal directly connected to the throttle. Nope, all new cars use the drive-by-wire method, and there's certainly some pros and cons to that. Anyway, as you can see, this is a very simple system, which is good because simple is always better. But in order to maximize the fuel economy on our project car, the driver needs to constantly watch the scan gauge and adjust the throttle. I think this is a job better suited for a robot if you ask me. So let's make this simple throttle a bit more complicated. And here's a drive-by-wire throttle body from a similar sized engine. This is actually a Delphi throttle body from an unknown car. I picked this up years ago. As you can see, it doesn't have provisions for a throttle cable, and the reason is there's an electric motor inside this gizmo, and the mini electric motor is what opens and closes the throttle. There's also dual throttle position sensors inside this thing for redundancy. And what that does is help detect a possible malfunction and prevent runaway throttle. Well, it's supposed to, but not always. So in the absence of a throttle cable, the drive-by-wire throttle body is still somewhat controlled by the accelerator pedal, like this one. But in this case, the accelerator pedal is basically a pedal connected to a potentiometer, and it converts the movement of the pedal directly into an electrical signal. The connection between the accelerator pedal and the throttle body, now that's where it gets complicated real fast. You see, it more or less takes a computer to interpret the accelerator pedal signal and convert it into a PWM signal to drive the H-bridge controller, and that's what moves the little motor inside the throttle body. On most, if not all cars, the PCM or ECM does all the heavy lifting and generates the signals automatically. Now, for me, the electronics and the code to make this thing work is simple stuff. On the other hand, getting all this stuff to fit the car and also keep the PCM happy, well, that's where it gets a little difficult. Let me walk you through some of the development I went through in order to work out some of the problems I could foresee. So the first thing we needed to do was a way to mount the drive-by-wire throttle body to the Saturn's intake manifold. So here we have the first part of the adapter. Now this thing is only part of the adapter. Well, there's actually an interference issue, and the adapter needs to be made in layers. Unfortunately, we'll need to add the idle air valve to the system. Now this is completely unnecessary, but the Saturn PCM is expecting this device to be present. So the idle air control system is basically just a little stepper motor, and when it's activated it moves this little prindle in and out. And by doing this, it regulates the amount of air bypassing the throttle. Basically, this is how the idle's maintained. Let's take a look at how this gizmo sort of works. So here we have it connected to the Saturn's electrical harness, and we just got it kind of hanging on top of the throttle body. Let me switch on the ignition system and allow this thingy to initialize. So as you can see, the prindle moved out and then back in, and then it moved to a position where it thinks it needs to be. Now, if the engine were running, we'd see a lot more activity, but for a quick demo, I think you get the picture. Now, let me do this again in case you missed it, but this time we'll do it in slow motion. And one more time, even slower. So that's the idle air control. We don't need it, but the Saturn's PCM is expecting to see it there. And we'll get some non-critical codes if we leave it out of the system. So the idle air control gets its bypass air from this hole here. Yep, it's unfiltered air. Meh, it'll be fine. Anyway, the air goes through the valve and ends up supplying the engine with a variable source of air in order to modulate the idle. The next layer we have to add is this adapter that mounts the drive-by-wire throttle body to the Saturn's engine. Now, I only show 2 bolts, but there's supposed to be an additional 2 bolts that go all the way through the 2 layers and cinch the whole thing together. So the throttle body just slides on, and at the end of the day all this junk bolts up to the engine without any issue. So all we need now is an accelerator pedal type thingy. Well, we have this thing. I believe I pulled this from a Chevy Cobalt a few years ago. It's okay, but I think it'll be a nightmare to mount this in the car, and I really don't like fiddling under the dashboard. Well, in usual fashion, I pretty much took matters in my own hands and designed a gizmo that would connect to the existing throttle cable and convert the mechanical action into an electrical signal. Now this thingy doesn't have a throttle return spring installed yet, so yeah, it doesn't return to the idle position. Not a big deal. The return spring, we'll deal with that later. Maybe. All this stuff is sort of overwhelming. I put a lot of time into the system, but I feel like it's overly complicated for basically a few experiments. I also have concerns about the idle air control valve. It's possible it won't work as expected, and then we'll have more delays. You know what? I think the best thing to do is grab all these parts and pitch them in the trash. Yeah, that's better. So now we're back to square one. It feels good to start over. I really can't afford to take the time to do this often, but sometimes after you work through a problem, the solution is, not so great. And getting the system to work is kind of like pushing sand up a hill. I think almost everything we need is right here in the original throttle body. Let me show you what I'm talking about. So all we really need to do is control the amount of air getting into the engine for this robotic throttle experiment. I propose we just stack the throttle bodies. Yeah, something like this. Of course, we'll need something to mate the 2 throttle bodies together, and for that I have a simple 3D printed adapter. It'll slip right onto the stock Saturn throttle body, like this, and I reckon at some point we can put a big hose clamp around here to hold this thing together a little bit better. Now, for the throttle butterfly, we can either leave it in place or we can easily remove it. Now, I'm sure there's a bunch of folks out there that'll say, "You can't remove that, Jimbo. And if you do, the throttle shaft will fall out." Nope, don't worry about that. The throttle shaft will not come out of this, even if you wanted it to. You see, it's pretty much pressed in there, and it doesn't come out, trust me. So anyways, like I said, we can either leave it in or take it out, it doesn't matter. So there you go, now we're getting somewhere. I think I mentioned before that the electronics and the code for this gizmo is the easy part. Now, let me show you how it works. So over here we have an Arduino Uno, and it's fitted with a terminal block shield for easy wiring. On the other side, we have a high current H-bridge motor driver, and I think this thing cost about $6. Anyway, this is the thing that'll drive the little motor inside the throttle body. To control this rig, we're going to use the throttle position sensor already attached to the Saturn's throttle body. And of course, the throttle cable from the accelerator pedal connects right up to this thing. So that pretty much takes care of the accelerator pedal input. Now the PCM will still be expecting a throttle position signal, and that's fine, we have that covered. This particular throttle body has 2 throttle position sensors. We'll need to use one for the Arduino feedback loop, and the other sensor we can send to the PCM. Now, fortunately on this throttle body, the 2 sensors are completely isolated. I think on most throttle bodies, the 2 sensors are electrically connected, and that would complicate things just a little bit, but in our case, no worries. So right here, you can see how I've prepped the throttle position wires that'll go to the Saturn's PCM. Alright, so let's connect the power. Now keep in mind this setup's running on the bench, and I made a few changes prior to shooting this video. The throttle is fluttering ever so slightly, and that's because I need to change the idle calibration numbers in the code. Not a big deal. So now you're saying, whoop-de-doo, double throttle bodies, how's that going to help? Keep in mind, it's the drive-by throttle body that'll be feeding the engine. If you can, pay no attention to the other throttle body. We're just using the stock Saturn throttle body as a mounting base, and we're using its throttle position sensor. Right now, the drive-by-wire throttle body exactly mimics the Saturn's throttle body, and that was my intent. You see, we obviously need for this throttle to work, and the first stage is just to mimic the other throttle body. So that's pretty much done. From this point, all the magic that I speak of will be in the code. Now, let's take a look at a snapshot from one of our previous fuel economy tests. So here we can see the scan gauge, and it's showing some very impressive numbers. Now, this snapshot was taken about 2.5 hours into the test, and the whole time I was behind the wheel, I had to constantly monitor this gauge. So my point is, I don't want to have to look at this scan gauge all the time. I just want to drive the car and have the computer do all the work. Yeah, I'm that lazy. So from my observations, the best fuel economy was achieved by holding the throttle in a position that gave map sensor readings between 7.8 and 8.4. To make a long story short, the map sensor is responsible for measuring the airflow in the engine. It's basically an analog signal, and we can use that signal to automatically adjust the throttle on the car for the best fuel economy. Basically, it's just math and some code. Now, don't confuse this with something like a cruise control. Nope, the driver still has full control over the throttle. However, when the system is active, the throttle input from the driver will be processed, and the actual throttle feeding the engine will limit the air intake for maximum fuel economy. Now, in the event I'm involved in a high-speed police chase, well, I'll also write a bit of code to allow the Saturn to evade the cops, if that's even possible. After all, it is a Saturn, and there are limits. What I mean to say is, I'll write the code to detect when the driver commands more throttle than is normal for steady-state cruise, and the system will respond by ignoring its primary objective, which is maximum fuel economy, and allow the engine to make as much power as possible, and thus possibly avoiding the authorities. So to sum it up, this drive-by-wire modification will automatically control the throttle for maximum fuel economy during our experiments, and will eliminate the need to constantly monitor the scan gauge. Hopefully this will help us find new ways to improve the fuel economy, especially with the lean burn system. Now, we still have a lot of testing to do with that. Now, as far as future experiments, well, this Saturn is scheduled for a diesel engine swap real soon, and quite frankly, I'm still having too much fun with these experiments. So what that means is, we need to work harder to finish these experiments. But since I'm under doctor's orders to take it easy for a while, this creates a problem. So technically, if I understand what the doctor was saying, I'm pretty sure he was suggesting that I need to buy another Saturn in order to keep the fuel economy experiments going and to still be able to do the diesel swap. So that's what we did. So this is a 1995 Saturn SW2. This car has survived on this planet for no less than 27 years and has only traveled a total of 156,000 miles. It's certainly in good shape for a local car. Typically these cars don't fare as well as this one did. I speculate it must have been garaged most of its life because the paint is actually mostly intact, with only the front and rear bumpers showing signs of deterioration. Now this car is a twin cam, and of course that means this engine has 2 camshafts. Let's see, 1 and 2. The twin cam engine makes about 25 more horsepower than the base single cam engine, but unfortunately the fuel economy is slightly lower. Whoever ordered this car knew, wow, they're my hero. This car was optioned exactly the way I would have ordered it back in the day. Let's see, full leather interior, 5-speed manual transmission, air conditioning, cruise control, and wind-up windows. You gotta love that. I hate power windows, and I guess someone else did as well. Now this car is not without its problems. The transmission has some issues, and it may need to be replaced. Hopefully the parts that I just ordered will be enough to save the gearbox, but we're prepared to replace it in any event. Over on the left side of the car, well, she's a little loose. This is actually a common problem, and it's just a broken locating rod. This car is nearly rust-free on the undercarriage, and that's certainly a huge bonus. Oh yeah, the left front fender was damaged when a deer ran into the car. The replacement fender seems to be a different color, and well, we'll fix that at some point. When it comes to Saturns, let's be honest, they're all ugly little ducklings, especially the Generation 1 Saturns. But I really do like the way the station wagon looks. You know something else? Actually, when you get right down to the details, it seems like the first generation Saturns, although ugly as hell, well, they seem to have a little bit better fit and finish. For example, the door handle on this car looks nice, but on the other hand, the door handles on Gen 2 and Gen 3 Saturns, well, they're just blobs of black plastic. I guess the only real disappointment is this car has the ultra rare leather interior, but the driver's seat will need to be replaced eventually, if I can find one. Anybody know where I can get a nice leather driver's seat? In this area of Kansas, Generation 1 Saturns ain't exactly growing on trees. Now, we did do some minor cleanup under the hood in order to work on the transmission. However, the car has been sitting a while and it needs a good cleaning, but I think it'll come around. Oh yeah, the alarm system. I had no idea this car was equipped with an aftermarket alarm system. Oof, those things, I tell you. Anyway, when we pulled the battery to work on the transmission, we somehow upset the alarm and the immobilizer kicked in. That was quite a surprise, and it took a little while, but we were able to completely remove the electrical tumor that was laced into the car's wire harness. These aftermarket alarms might seem like a good idea, but they're a big problem when they get all goofy and stop working. Good riddance to this thing. I think I've rambled on long enough. I apologize for not getting any testing done in today's episode, but frankly it's just too hot to spend a few hours behind the wheel of the project car. Anyway, we'll see you next time.
Twin cam!